All right, it is all yours.
Awesome. Hey, everyone. So I'm Mike Blakely, and I'm going to talk about what I do, which is engineering internet encryptors. And if you have no idea what that means, stay tuned and I will explain it for you. All right, let me figure out where I change charts. Okay, so a couple things that you're going to be able to learn today is we'll talk about what's important about securing our communications. I'll explain encryption in about 5 minutes or less. And I'll talk about all the different kind of engineering that goes into developing an internet encryptor. But I'll start with a little bit about me. I am a local. I grew up in Solana Beach. I went to Earl Warren. I went to Torrey Pines High School. And then I went off to Cal Poly and I earned an electrical engineering degree. And then I went to UCLA and got a master's degree in communications theory, which is about, communicating via cell phones and satellites and things like that. I spent 13 years working for a company called Hughes Network Systems in Sorrento Valley. And most of the things I did there were products that helped people communicate over satellites or over cell phone systems. So that little blue phone there was actually a phone that worked over like a cell phone. But if there was no cell coverage, it would complete the call by going all the way up to a satellite. Those big satellite dishes on the right, that's how some third world countries that didn't have any fiber optic connections used to get their telephone service into and out of the country, was all via satellite. And I would design the electronics that did that. And I designed the first OnStar box with part of a team that did that, that went into the first Cadillacs that had OnStar service. Today I work for a company called Viasat, and it's up in Carlsbad. And my job there has been a program manager where I would lead a team of engineers, electrical engineers, software engineers, mechanical engineers, test engineers, to design products that would allow people to communicate securely. I made internet encryptors like we're going to talk about today. I made boxes that helped people on airplanes communicate securely with people on the ground. I made equipment that helped the electric grid to operate securely, such that the people at SDG&E's operations center could check on all the equipment and all the electrical substations and control it and make sure it's operating correctly and keeps the hackers out. And now I'm what's called a business director, and so I actually have multiple teams of engineers that are working under program managers, and my job now is to develop all sorts of new products that I think my customers will find useful and build those in a factory and sell them to the users. So I'm going to tell you how I got into engineering, because I think that's actually really, really important for an intro to engineering class. Why did I do this? And when I first started, I didn't think I wanted to be an engineer. I thought I wanted to be a doctor because my dad was a doctor. And that just seemed really fun. So when I was in junior high, I thought I would probably be a doctor. But I did always love figuring out how things worked. I like to take things apart and see what was inside and try and figure out how did all the latches and springs and electronics work. I enjoyed playing around with programming on computers. When I was in junior high and high school, I had a computer, but computers were very rare. This was the first computer I had back in 1977, woefully underpowered compared to, the cell phone you all have in your pocket today. But it was an opportunity for me to get the computer to do something. I could program a game and then play it. I could program it to solve math functions. And eventually I started ordering through the mail, because there was no internet yet, electronic components that I could add into my computer to make it higher performance. And sometimes to add those components, it wasn't just plugging it in, like plugging a memory card into a phone. It was like, cut these wires and unplug these components and unsolder something here and then put this other stuff in. And so there was always great fear in my heart that when I was done, it wouldn't work and I would have broken my computer. But luckily, everything continued to work. And I think that helped inspire my desire to do engineering. When I was a senior in high school, I was the office gopher, meaning Mike, go for coffee. Mike, go for lunch. Mike, go to Home Depot and get this stuff we need. I just non-engineering things in the office. But it was a software company. It's down in Sereno Valley, and I could see how they did their engineering and how this team designed and built software. And I really liked the collaborative problem-solving atmosphere. I said, this is a neat vibe. I could work like this. And so I think that helped me also want to be an engineer. And finally, my dad, knowing that I was also thinking about being a doctor, invited me in high school to come watch him do surgery. And so he put me in the gowns and everything and the mask and sat me in the corner of the operating room while he was doing surgery. And I just about fainted. I thought the inside of the body was really cool looking, but something about the blood and everything else just made me really queasy, and so that was the end of my my aspiring doctor career. All right, so let's talk for a minute about communicating on cell phones and communicating online and on the internet, and what kind of security expectations we have. So this is a question to you guys. Somebody speak up. What expectations do you have? Why do we want secure communications?
Anybody?
Oh, hold on. I got to turn up my volume. Okay, say that again.
Oh, I was saying anybody. Anybody got a question? Come on.
Oh, okay. It was Mr. Friday.
Yeah, what do you say?
He's trying to answer a question, or we're trying to answer a question?
He's asking you guys.
What's the question?
Yeah. What expectations do you have when you're on your cell phone or when you're on the internet about privacy and security?
I don't want the government to know what I'm doing on my phone.
Okay, that's a good one. What else?
What'd you say?
I don't like it when people hack into my Netflix or like my Amazon.
Yeah.
People always try to hack into that.
Really?
Okay. I don't want hackers to take over my accounts and use my services I'm paying for. That's a good one. Anybody else?
People hack into the gram. Yeah. Personal information, personal text, all that. Yeah.
Okay.
DMs and then they're hacking it. Yeah.
Yeah, I don't want my personal information. So it's interesting because a lot of the things you guys just described, it's about keeping things private, right? Which a lot of times when we talk about encryption, you think of that as this is how I keep things private, is I encrypt it so nobody can read it. But part of it is also about really making sure who you're talking to and things like that. So we're going to walk through an example here. We have Alice. She's a consumer. She would like to buy some diamond earrings for somebody as a gift, and she's going online to do so. Bob is the retailer. He runs an e-commerce site and he sells jewelry. And Chuck is the bad guy. Chuck's just trying to make a buck any way he can by hacking on the internet and trying to steal credit card numbers. Pardon?
Are these real people, or did you just?
So here's the funny thing: is if you go and you start doing research on internet security and encryption and things like that, they always use Alice, Bob, and Chuck as the two good guys and the bad guy in all the examples. So I didn't make it up. It's just what everybody started doing. So if anybody's named Alice and Bob, great. If your name's Chuck, hey, I'm sorry, man. All right. So first of all, Alice expects confidentiality. She doesn't want Chuck to be able to see her credit card number, okay? Because then he can take it and go buy stuff and she'll get the bill. Alice expects availability, which means she doesn't want her communications to Bob over the internet to be blocked or unavailable. She wants to be able to make the purchase when she wants to make the purchase. She expects Bob's website to be authentic, right? She wants to know that she's talking to the real Bob and that she's not talking to a spoofed website that Chuck created that looks like Bob's but isn't really Bob's and is just there to steal her information. Alice expects integrity, which means her order doesn't get tampered with while it's going back and forth on the internet. If she orders one pair of earrings, she doesn't want Chuck to change that to an order for 10 pair of earrings and then show up on her doorstep and steal 9 and leave 1. And Alice doesn't realize what happened until she gets her credit card bill at the end of the month. And finally, there's something called non-repudiation, which means you can't lie and say you didn't do it. Alice can't lie and say, I never ordered those earrings, Bob. Why are you charging my credit card? Give me my money back. Because Bob has some kind of evidence that shows that Alice actually made the order, and it's something that would stand up in court if Alice were to challenge it. So these are kind of the nuances of ways that we want to protect ourselves when we're communicating electronically. So just real quick, something real basic to understand. Computers at their heart really only know 2 numbers, 0s and 1s. And they represent every piece of information they're handling with just a bunch of 0s and 1s. Everything has to get broken down that way. So if a computer is representing numbers and letters, there's a series of 0s and 1s that they use to represent each number and letter. I'm showing those on the screen there. If they're representing colors, something they're showing you on the screen, each color has to be represented some way by a series of 1s and 0s. If they're representing audio, like me talking to you right now, everything I'm saying is getting decomposed into a bunch of 1s and 0s and streamed over the internet to you and put back together and sent out of a speaker so that you can hear me. Everything's 1s and 0s in a computer. So when we talk about encryption, and here's your 5-minute introduction to encryption, we're talking 1s and 0s. So this little chip here has the ability to basically do just a little bit of logic. If you put 2 0s into that chip, it'll give you a 0. And that's what the thing at the top is showing you. If I put in a 1 and a 0, like the 2 middle examples, it's going to give me a 1. And if I put in 2 1s, it's going to give me a 0. That's all this little chip does. It takes 2 inputs and it does this little transformation and gives you 1 output. But it's at the core of all encryption. Let me show you how. So I have some data. It's 16 digits, and you can see it in the data block there, a set of 16 0s and 1s. Now, when we want to encrypt something, we need a key, okay? For example, when you guys are accessing the web, sometimes on your web browser, there's the little lock icon. Who can tell me what the little lock icon means? When you're browsing the web, what's the little lock icon mean? You guys should all know this.
The
Pardon?
flag?
Say again?
It's secure.
It's secure, right? It means your communications with that website are secure. It means they're encrypted. And a lot of times what you may see is when you first get to the website, the lock is open, okay? And then when you finally get to the point of the website where you're going to make a payment, the lock is closed, okay? And in order for the lock to be closed, your computer and the website have to exchange a key and then start doing the encryption. And so that's one of the important parts of the key there. So I built my own key here. It's just a random series of 0s and 1s I made up. And what this little logic gate is going to do is we're going to send these digits in 1 pair at a time, and it's going to give us the outputs. And I color coded it so you can kind of follow along. So first we're going to send in the 2 red 0s, 1 from the data line, 1 from the key line. And in the encrypted data output, we see a 0. Then we're going to send in the first 2 yellow ones, a 0 and a 1. It's going to give us a 1 on the output. We're going to send in the 2 green ones, a 0 and a 1. It's going to give us a 1 on the output. We're going to send in the 2 blue ones, both 0s. It's going to give us a 0 on the output. We're going to send in the 2 purple ones, 2 1s, and it's going to give us a 0 on the output. Just like the bottom transform shows us up by that chip there. Okay, and so that just keeps going. You guys can easily do that on your own afterwards. This is simple. But if you look at the encrypted data, it doesn't look like our input data block, and it doesn't look like our key. It's different from both, okay? And that's what's important. The encrypted data should look different from what we're trying to protect. But here's what's neat about this little logic transform and about the key, is if I now at the other end of the communications link, take the same key and the encrypted data and run it through the same transform, the original data comes back out. So that's the cool thing about encryption, is it's easy to reverse the process and get the real data back. Now, this is a super simple model, and how our real encryption works today is a lot more complicated. There's a lot more munging and mixing up of the data and the key on the input side, and sometimes you run the same data through multiple times with different parts of the key in order to get a more complex encryption. But in the end, at the very heart, there's this little logic transform. So yeah, this is kind of like a block diagram of what really happens today. And the keys are a lot bigger, 128 digits or 256 digits. So this is a real world example. This will be the end of our encryption primer. I have a credit card number on the left there. Sorry, it's not really my number. I just made it up. And I decompose that number into the ones and zeros that the computer understands, how the computer would decompose it. Okay, and then I made up a 128-bit key that's up in the top. And then I put them both into what's called AES encryption. That's the most popular type of encryption that's used everywhere right now. And what comes out is all of the digits on the right. If you were to compare them digit by digit to the credit card number, they look absolutely nothing like the credit card number. And if I were trying to reconstitute those digits into the characters that the computer would display to us, it would show us the characters on the bottom in that little green box, which not only are those no longer numbers in terms of how the computer represents information, it doesn't even look like letters. It looks like gobbledygook.
Hey, Mike.
Yeah.
I think we missed that slide with the gobbledygook, like the slide that actually shows us. Yeah, there we go.
Did it just come through?
Yeah.
Okay. So we got the credit card number on the left. We got the 128-bit key on the top. We've got the data that comes out on the right, and then on the bottom, the little green box is the gobbledygook. All right. So just so I get a feel, Mr. Friday, I'm going to advance the slide here. Tell me how long before you see a change there.
Okay, I will.
Okay. So all right. So let's talk about what is engineering. So to me, these are Mike's definitions, right? So engineering is applying scientific knowledge to solve real world problems. Whether you're building a bridge to get across a chasm, whether you're building a car so that you can rapidly get from place to place, whether you're building a cell phone so that you can communicate with somebody else, you're solving somebody's problems. I need to get from here to there. I need to communicate with somebody using science and knowledge. We're using physics, metallurgy, thermodynamics, electronics, acoustics, chemistry and biology, all of these things to solve problems and to create products. Engineering is to me is also just the simple idea of designing and building a product or a machine or a structure. But in that building process, we do analysis, we do math, we do numbers to figure out what is the optimum set of capabilities for the end user. I could build you the best, fastest, coolest smartphone, but it would be so big it would never fit in your pocket or even your backpack. So that doesn't do you any good. That's not an optimum set of capabilities. It's too fast and too powerful. It's fast and powerful, but it's too big. So we have to make it a little slower, a little less capable, but now it fits in your pocket, and that's the optimum set of capabilities. So we're going to walk through some of the engineering and some of the analysis and capabilities that I do. This is one of my products. It's a network encryptor. So the government uses this in, for example, their embassies, okay? So there's an American embassy in China. They need to be able to communicate with the government in Washington, D.C. So they put one of these in the embassy in China. They put one of these in the State Department in Washington, D.C. All the internet communications between those two places go through this box, and this box encrypts the data, authenticates the users on both ends, makes sure that the data is not tampered with. All of those things we looked at with Alice, Bob, and Chuck.
Okay, so we're still a little behind. We're down at the bottom of the engineering slide,
Okay.
but we haven't seen, the box hasn't presented itself as yet.
All right.
So I just wanted to, oh, here we go. Boom, we're on.
Sometimes if you let me know that, I can go forward and back an image, and it kind of forces the image to come through. So give me the feedback.
Oh, for sure.
Okay. So this thing, it's probably about a foot wide, about a foot deep, a couple inches tall. It's made of metal. It's completely sealed up, so there's no way to get inside the box so that nobody can tamper with it. And it runs very, very quickly. My internet connection here at home is 200 megabit per second. This box runs at 1000 megabit per second. So some people, I think if you've got the fastest internet you can get into a house, you might have 1000 megabit per second, but most people don't in their home yet. But that's how fast this runs, which, if you've got an embassy full of people, you may have several of these in order to have enough capacity for all the internet you've got going in and out. All right, so what kind of engineering goes into this? Well, first I got to figure out, what does the box need to do? And a lot of that engineering is really talking to your end user. What do you need the box to do? How fast do you need it to go? How big or small does it need to be? How do you want to be able to control and interact with it? And figuring out, how do I then design a product and engineer a product that does what my customer wants it to do? There's all sorts of performance trade-offs that we do in engineering. How fast does it go? This one goes 1000 megabits per second. As a result, it consumes a certain amount of power. If somebody needs a lower power device because maybe they want to run it off a battery in a vehicle, they may need a slower data rate in order to not use up all their battery all at once. When electronics run faster, they generate more heat. And in order to keep the box from burning up, I need to have either a fan, or I need to have a lot of metal in the enclosure in order to kind of soak up that heat and radiate it out into the air. And that makes my box larger and more heavy. So again, if somebody's looking for a more portable device, maybe even something they could carry on their person, I might need to slow the data rate down a lot in order to not generate so much heat that the box burns up or is too hot to hold. And size comes into play there as well. Cost is a big factor. I can design I think Apple's a great example here, right? iPhone 10, 11, 12, these are really high performance products, but they've gotten to a price point that's over $1,000. And I think that's made it inaccessible to a lot of people. And so it's really important when you're engineering a product to understand who's going to buy your product and how much can they afford to pay, and make sure that you're designing it to hit their price point as well as the minimum capability that they need. Then there's manufacturability. When you make things smaller and squeeze the electronics closer together, they're more difficult to manufacture, and the manufacturing cost goes up. And so that's another thing to think about when you're designing a product and making choices about how big it is. There's other things that we look at in terms of complexity, and are we going to buy software or write software, and what else we're going to do. So we're going to go through 4 different kinds of engineering. We're going to go through electrical engineering, mechanical engineering, software integration, and test engineering, and kind of talk about how those apply to the box we have here. So first thing, trying to show you a picture of a circuit card. So hopefully that comes up, the green circuit card.
But it's probably going to lag by like half a minute or so.
Okay.
But
so I imagine that you've all at some point seen the inside of a computer, the inside of a cell phone, the inside of some product, and seen, you know, little circuit cards in there. Sometimes they're blue, sometimes they're green, but all the little parts on them looks like a little city. And you know, what the electrical engineer needs to do is figure out, what do I want to do, and what parts do I need to choose, and how do I connect all those parts together to build that little circuit card. And so part of the engineering task is you know, learning about what do the different parts do. You know, some of those parts are microprocessors. You know, do I want an Intel microprocessor? Do I want an AMD? Do I want something else? You know, what's the right part I need? Some of those little integrated circuits are for communicating. Some communicate over wires like Ethernet. Some communicate wirelessly like Wi-Fi or Bluetooth or cell phone. And so you need to figure out, well, how, you know, if my box needs to communicate with the outside world, you know, how do I want it to communicate, and what kind of chip do I need there? Some chips are used to convert outside worlds and signals to those ones and zeros that computers understand. There's chips that take the signal from a microphone that grabs voice and audio and converts it to ones and zeros. There's other chips that take the ones and zeros and convert it to a signal, so you can put it into a speaker or put it onto a computer monitor. And so once you've identified all the different parts you need, you then need to use a series of computer programs to connect those parts together and lay those parts out onto a circuit card, and ultimately then send that information off to somebody who can manufacture the circuit card for you. And that's how that stuff gets done. So now I'm going to go to the mechanical engineering chart. Let me know when that comes up, Mr. Friday.
Okay, I will.
And so mechanical engineering is about the physical structures that we're making. You know, could be a bicycle frame, could be the case for my cell phone. It could be the frame that holds my computer monitor together. You know, it's things made of plastic and metal and glass and rubber. And how do we design all these things and put them together in order to hold and protect the thing that we're making? So when I'm making my internet encryptors, I'm thinking about several things. One, I'm thinking that these are sometimes used in rugged environments, like on Humvees or in airplanes. So they need to be rugged. You need to be able, you know, a soldier needs to be able to drop them and it can't break. Number two, I have high performance products and they generate a lot of heat. So I need a lot of metal in them in order to get the heat out of the box. Number three, sometimes they're used in really difficult environments. Could be used in a battlefield command post in the desert in Iraq, where there's lots of dust and sand and there's not a lot of protection. And so I need to make sure that there's no seams or gaps where sand can get in. So now I'm using lots of rubber gaskets and O-rings and things to seal up all the parts there. And so, and I need to make sure, you know, I talked about a lot of metal to get the heat out. So mechanical engineers, you know, they're designing using computers. What does the metal and plastic and stuff need to look like? How does it all go together? Do I use screws or tabs? And then they need to do the analysis. This is the part where the numbers come in. And these days you can use computers to really model the electronics. How much heat is going to be coming out of my electronics, and then how is that heat going to be distributed by the metal chassis, and what sort of temperatures are we going to result with? You know, like how hot is the top of the chassis going to be? You know, because I don't want to burn my end user. And how hot are the electronics going to be? Because if they get too hot, they're going to burn up. And so if the picture came through on the right side there, that's a thermal analysis program running on a computer program where somebody has modeled the electronic circuit card and they've modeled the enclosure, and it's showing you via the different colors, with red being hot, purple being cold, how hot the various components are getting. And then the other kind of analysis mechanical engineers do is structural analysis, right? So, you know, when they design something, and it gets moved and dropped and shoved and things, it's going to experience forces, and we want to make sure those forces aren't so strong that they damage the component. And so the bottom left picture with that big colorful T-shaped thing, you know, that's a piece of metal that somebody has modeled on a computer, and you can see the 3 arrows on the left side. That's a force that they're modeling on the computer pushing down on that piece of metal, and the colors are showing the tension in the metal. And you know, if you get too much tension there, your metal is going to deform, or even worse, it's going to break. And so you want to be able to measure that tension and make sure that it's going to be low enough that your metal is not going to break. Or if it's plastic, it'll be, you know, lower numbers that it can tolerate. So this is what the mechanical engineer does. All right, so going next to the software page. So software engineers, they need to figure out, you know, what does the computer inside this thing need to do? So in my case, I have a internet encryptor. So my software needs to do several things. It needs to take all of the information coming in from the embassy computers, and it needs to encrypt that data. But I also need to be able to load a key into there that I can use for the encryption. In general, it's good practice to not use a key for too long, just in case a bad guy, Chuck, figures out what your key is and can then decrypt your communications. So in general, we only use a key for a day or a week. And so somehow I need to be able to communicate to my user, hey, your keys are about to expire. You better load some more keys in. These are all things that my software does. And so a software engineer, they kind of make these lists of, these are all the things the software needs to do, and kind of breaks it into a bunch of small functions and capabilities. And then they actually code each one of those up on the computer. And then the most important thing is then they have to go test it. Not only do they have to test that all the normal cases work, but they have to test all the abnormal cases, right? You know, if my internet encryptor is designed to take in a 128-digit key, what if the user tries to put in a 129-digit key? How's my software going to respond to that? Am I just going to use the first 128 digits and not tell anyone? Or am I going to give the user an answer that says, hey, wait a minute, something bad happened here. What do you really want me to do? You know, so there's all those, you know, error cases that you need to deal with. You know, how does your cell phone respond when the Wi-Fi goes out? It's really nice when it just switches over to the mobile network, right? Somebody had to write the software that's constantly monitoring the Wi-Fi and then switches over when something happens. So once we've done and I'm on the next chart here now with some people in a lab.
Okay, yeah, we're still on the software design and coding page. Yeah.
So once we've designed the electronics and we've written the software and we've designed the enclosure and we've built all these things in a factory, we need to put them all together and make our product work. And that's the integration and testing piece. And so part of it is powering up our electronics, testing them and making sure they work, loading the software onto the microprocessors on our electronics and trying it out and seeing if it works. And it never works the first time. And then you've got to do what's called debugging, which is basically problem solving, is where is my software going awry? What's causing it to do that? And what changes do I have to make to fix it? Once things are kind of working, like with my internet encryptor, once it seems like it's basically encrypting data at a slow speed, now I need to verify my requirements. That means all of the list of things that the user wanted it to do, I need to test every one of those and make sure it's working correctly. Can I encrypt data? Can I decrypt data? Can I load a key? Can I set an expiration date for the key? Can I load multiple keys? Can all of the different error messages and notifications from the encryptor be displayed back to me on my screen correctly? We have to do something that I call parametric testing. That's does it actually meet the numbers that I said it's supposed to meet? For example, my encryptor is supposed to be able to run as fast as 1,000 megabits per second. Well, I need to test and make sure it really does that. Because if it's only running at 997 megabits per second, you know, my end users may be frustrated by that. They paid for 1,000, they want 1,000. I need to measure how much power it's consuming and make sure that it's not consuming more power than what I designed it for and what I'm advertising. Because my customers have to, plan how much power they're going to provide for this device. And then finally, as we're designing products and writing software and debugging and solving problems, we're actually doing this for often several months at a time. And so we want to make sure that when we fix one problem, we don't break something else. And so we actually do a lot of we design computer programs that will just test our product over and over and over again, with the goal of wanting to test all night long, every night. And that way we make sure that nothing's broken and we have a really robust and high quality product. Once everything's working on our product, we're not done. Now we've got to go build hundreds or thousands of those in a factory and ship them to our end users, our customers. And so that's a whole nother set of engineering, manufacturing engineering, industrial engineering, process engineering, quality assurance engineering. And these are the engineers that are designing the factory floor to build our product. They're designing the testers that can test hundreds or thousands of units of product every hour or every day so that we can do volume production. They're sampling all of the data from the manufacturing equipment to make sure that there's no manufacturing defects. And if there are defects, to really figure out what's the cause of the defect and how do we change the design or change the manufacturing approach to avoid those defects. And so those are all extremely important engineering disciplines as well. So you have an incredible advantage that I didn't have. I got started in engineering because I like to take things apart and try and figure out how they worked. And I did a little bit of programming on a really primitive computer back in 1977 and 78. Now engineering is so mainstream and there's so many tools available that for very small investment in time or money, or even free, you can do all sorts of things and kind of try engineering and figure out, is this for me? If you want to write software, if you want to code, there's all sorts of coding camp and coding websites that'll teach you how to code online and walk you through projects and things like that. You can buy super cheap electronics. This little thing here called the Res. Do you guys have you have the why and where to start chart up, Mr. Friday?
No, we're still waiting to switch off of the integration and testing.
Okay.
It's a little bit laggy, but it's coming.
All right. So
and while we wait, by the way, I do have a Raspberry Pi. Yeah. I got one.
Excellent. So Raspberry Pi is a $35 computer that you can program, and it's got a lot of interfaces that you can interact with the outside world. And so people use that for all sorts of projects. And if you buy a Raspberry Pi and go online, there's hundreds and thousands of projects that you can create. Robotics is a great place to start, whether it's Lego robotics in your own house or whether it's a robotics team at the high school. Smartphone apps are another great place. Almost everybody's got a smartphone, and it's really easy to go online and figure out how to code up your own apps. And another great way to try mechanical engineering is with a 3D printer. You can design and build stuff all on your own. My son is a tuba player, and when he was in college, he and the other tuba players would use computers to design tuba mouthpieces, fabricate them on 3D printers, and basically they were experimenting to try and find the loudest possible mouthpiece that could be created. All right, so we got about 4 minutes left. I want to give you guys an opportunity. If you've got questions, I'm happy to field those, and then I'll do a quick wrap up.
Any questions? Anybody got any questions? Go ahead.
What specific skills and knowledge do you think a person should have when being a certain type of engineer that you are?
So I think that curiosity and problem solving are probably two of the most important traits that make you a good engineer. And then, some engineering disciplines, electrical engineering, mechanical engineering, there's a lot of math involved. And so the math skills are good. Other engineering disciplines like software and things like that, sometimes it's more the ability to solve a logic problem and to break problems down into small tasks are more important than the math.
Yeah, I think engineering is really great for me. My background is physics, so I got the opportunity before I got into education to work for 3 startup companies, 3 Caltech-based startup companies. And what I liked when I looked at engineering was the fact that you've got a problem, but you don't quite know the route to the solution. So it's almost like freedom, like you're using your mind and the tools you have to come up, take yourself from problem to solution.
Mm-hmm.
I think that's pretty cool about engineering.
I would say one of the most gratifying moments of my engineering career was, I designed that phone that works over a satellite when there's no cellular service. And I saw a news clip of an injured soldier in Iraq calling his wife on that phone to tell her that he was injured, but he was going to be okay. And that, she knew he was all right. And that just warmed my heart to know that I could be part of that exchange between that husband and wife.
Oh, that's pretty cool. More questions? Anybody else? Man, you guys are so quiet. Where's my questions like who is Chuck and all of that sort of stuff?
That was good. I like that. Where did those come from?
That was a good question. We need more like that. Nobody?
All right. I think there's only like a minute left, right, Mr. Friday?
Yeah, there's only a minute left, but thank you so much for sharing your knowledge and sharing with us in this class. I think it's great when we have a speaker like you to motivate us, to get into, to really look at this new field or a new field for ourselves, which is engineering. So thanks, and I think I'll sign off for now.
All right, you're welcome. Bye-bye.
All right, bye-bye. All right, everybody else, see you guys. You guys can log out. Go for your next class or wrap up.